Night falls long before history begins, and somewhere on a Paleolithic plain, a small group of humans looks up, unaware that their silent wonder is the first line in a story that will stretch across tens of thousands of years. Above them, the sky is a river of light, the Milky Way, a pale, foaming band that seems to divide the heavens in two, and although these early skywatchers have no names for constellations and no mathematics to describe orbits, they sense, with that raw animal intuition sharpened by survival, that what hangs over their heads is so regular, so strangely ordered, that it cannot be mere background to their lives, but a kind of cosmic clock to which everything around them obediently ticks. They notice that certain points of light never move with respect to one another, forming patterns that rise and set in the same order every year, while a few rebellious lights wander among them, meandering slowly along paths that defy the fixed tapestry of the stars. They watch the phases of the moon swell and fade in a cycle that seems to echo birth, growth, decay, and death, and though they cannot yet inscribe their thoughts into stone or clay, they transfer their impressions from one generation to the next as stories around the fire, tales in which the brightest stars become ancestors, predators, guardians, or judges looking down upon the fragile world below. When the first stones are raised at places like Nabta Playa in the Nubian desert, or at the far more famous Stonehenge on the chalk plains of southern Britain, the human gaze has already learned to track the returning points of sunrise and sunset, so that upright slabs begin to align with solstices and equinoxes, marking with eerie precision those turning points of the year when the sun seems to hesitate before retreating or advancing along the horizon. In these alignments, you can almost hear the unspoken question humming through early agricultural societies. Why is the celestial rhythm so precise when the earth below is so chaotic? And what hidden order lies behind the cycling of seasons, floods, and droughts? In Mesopotamia, where the Tigris and Euphrates carve fertile crescents through an otherwise unforgiving landscape, priests climb ziggurats and turn their eyes outward, turning naked-eye astronomy into a discipline of power. Clay tablets from Babylon and Ur record the risings and settings of Venus, the times of eclipses, and the omens associated with the strange behaviour of the wandering stars. Because to these early skywatch, centuries pass, dynasties rise and fall, but the scribes keep writing, and by about the first millennium BCE, Babylonian astronomers have noticed something profoundly practical amid the divine theatre. Eclipses repeat in a cycle of about 18 years, a pattern that later scholars will call the Saros. With this discovery, prediction enters the cosmic story. And what had been sheer terror, the sudden darkening of the sun in the middle of the day, becomes an event that can be anticipated, explained in terms of gods perhaps, but framed in a precise timetable etched into clay. Yet even as they catalogue the paths of planets and perfect methods to forecast their positions, a deeper enigma refuses to yield. What are these lights actually made of? How far away are they, and why do some among them abruptly appear, blaze for weeks, and then fade back into non-existence like sparks flying from an unseen anvil? A damaged cuneiform tablet from around 1300 BCE may record a guest star shining above the horizon, a supernova perhaps, but for its observers this sudden wound in the firmament is less a clue to the violent life cycle of stars than an omen of royal upheaval. The notion that such transient lights are distant suns tearing themselves apart will not surface for over 2 millennia. Down the Nile, Egyptian priests stand in temple courtyards and wait for a single star to pierce the pre-dawn glow. Sirius, which reappears each year just as the river begins to rise, becomes their celestial herald of inundation, and the Egyptian civil calendar arranges its 365 days around the rhythm of the star's heliacal rising. Colossal temples at Karnak and Abu Simbel orient their axes toward the sunrise on specific feast days, as if the stones themselves are turning to acknowledge some invisible cosmic presence. Yet for all their architectural precision, Egyptian skywatchers do not attempt the abstract geometry that will later define Greek cosmology. For them, the sky is a great river on which gods sail, the earth a stage on which they briefly walk, and the relation between above and below is one of symbolic reflection rather than mechanical causality. Far to the east, Chinese officials are also watching, but with a bureaucrat's intensity, because in imperial China, celestial phenomena are state business. Court astronomers of the Shang, Zhou, and later dynasties compile meticulous records of comets, eclipses, and novae, fearful that failing to predict an eclipse could be interpreted as political incompetence worthy of punishment. bamboo slips and later paper scrolls preserve accounts of guest stars, including the one that will burst into the sky in 1054 and leave behind the Crab Nebula, and because these chroniclers are less concerned with mythic storytelling than with accurate documentation, their records will become invaluable to modern astrophysicists trying to date and model ancient stellar explosions. Across the ocean, on the high plateaus and jungles of Mesoamerica, Maya astronomer priests build stepped pyramids that double as observatories, tracing the complex dance of Venus with a precision matched only by the Babylonians. Their codices, some of which miraculously survive fire and conquest, contain tables that predict the synodic cycle of Venus to an accuracy of a single day over centuries, because they believe that the planet's appearance and disappearance in the dawn and evening skies governs warfare and ritual. Here again, the heavens and human fate interlace like vines, and the mystery is not abstract. What is the universe made of, but urgent? How does one align human action with a cosmic order that seems both exquisitely regular and violently unpredictable? In these ancient civilizations, we see a pattern that will repeat in different guises. The sharper the eye for celestial regularity, the greater the need to impose meaning upon it, and the more precisely the heavens can be forecast, the more piercing becomes the question of why they possess such order in the first place. It is in the Greek-speaking world of the first millennium BCE that curiosity begins, cautiously at first, to detach itself from direct service to kings and temples and pursue the heavens for their own sake, treating them as a realm that might be explained not by moods of gods but by principles that hold everywhere and always. Philosophers like Thales and Anaximander propose that the cosmos is a natural system governed by intelligible rules, and when Pythagoras' followers notice that musical harmony can be described by simple numerical ratios, they begin to suspect that number and geometry are the keys with which to unlock the celestial machinery. The Earth, they argue, must be a sphere, because the shadow it casts on the moon during a lunar eclipse is always round, and because ships vanish hull first over the horizon. Once that conceptual leap is taken, it becomes possible to envision the entire cosmos as a nested series of concentric spheres, each carrying a planet or the sun and moon, all rotating around a central Earth where humans dwell. Plato and Aristotle refine this into a grand architecture of crystalline spheres, with the outermost realm of fixed stars forming an almost sacred boundary between the world of change and the realm of eternal perfection. And within this scheme, the wandering stars, planetae, trace intricate loops and reversals against the background of the zodiac, their retrograde motions demanding more complex geometric constructions to preserve the ideal of uniform circular motion. The great synthesizer of this vision is Claudius Ptolemy, working in Alexandria in the 2nd century CE, who gathers centuries of observations into his Almagest and constructs a mathematical apparatus of deferents and epicycles so flexible that it can match planetary positions with astonishing accuracy, provided one is willing to keep adjusting parameters. Through Ptolemy, the universe becomes a meticulously tuned celestial clock built entirely from circles upon circles, with Earth immobile at its hub, and for over 1,000 years this mechanical yet Earth-centered system will rule the learned imagination from the Mediterranean to medieval Europe and the Islamic world. Yet even within Hellenistic thought, seeds of an alternative vision are quietly sown. Aristarchus of Samos, in the 3rd century BCE, argues on geometrical grounds that the Sun is much larger than Earth, and that it makes more sense for Earth to circle the Sun than the other way around, but his work survives only in references and is largely ignored, perhaps because such a rearrangement of the cosmos feels philosophically and theologically destabilizing. The more one insists that the heavens embody perfection and permanence, the harder it becomes to admit that Earth might be just one more moving body in a vastly larger system. The mystery of the universe's true structure is already pressing against the confines of inherited metaphors. While the Latin West will spend centuries recovering and retransmitting Greek thought, other cultures take the astronomical torch and carry it forward in their own directions. In India, scholars like Aryabhata in the 5th century and Brahmagupta in the 7th develop sophisticated models for planetary motion, approximate the value of P with impressive accuracy, and even propose that Earth rotates on its axis, an idea also known among some earlier Greek thinkers but not widely adopted. They produce sine tables and algorithms that will later filter into Arabic astronomy, intertwining trigonometry with cosmic description. In the Islamic Golden Age, beginning in the 8th century, Abbasid caliphs in Baghdad sponsored the translation of Greek scientific works into Arabic, and the House of Wisdom becomes a centre where Ptolemy's geocentric framework is critiqued, extended, and refined by scholars who respect its power but are acutely aware of its anomalies. Figures like al-Battani, operating in the 9th and 10th centuries, measure the length of the year and the obliquity of the ecliptic more accurately than Ptolemy, while Ibn al-Haytham, al-Hazn, develops a rigorous theory of vision and experimental methods that will later influence European science. Meanwhile, one such innovation is the Tusi couple, devised by Nasir al-Din al-Tusi in the 13th century, a clever geometric construction that generates linear motion from two circles and later shows up, almost verbatim, in the planetary models of a Polish canon named Nicholas Copernicus. Through such invisible threads, the intellectual legacy of the Islamic world seeps into Renaissance Europe, where it will quietly undermine the complacent grip of medieval cosmology. In Christian Europe, after the fall of Rome, astronomical learning initially retreats into monastic scriptoria, where the night sky is mainly consulted to calculate liturgical dates and to embellish theological narratives with symbolic stars and planets. Yet by the 12th and 13th centuries, as translations from Arabic and Greek flood into universities, the Aristotelian Ptolemaic cosmos is integrated into a grand scholastic synthesis in which the nested celestial spheres become not just physical structures but metaphors for spiritual ascent, immortalized in Dante's Divine Comedy. In this layered universe, Earth's central position is not a mark of honour but of corruption and heaviness. Above the moon lies a realm of incorruptible ether where change is gentle and periodic, never violent, and beyond the sphere of fixed stars stretches the Empyrean, the abode of God, utterly beyond physical investigation. For the medieval mind, the greatest mystery is not the size or age of the cosmos, but how a finite, mutable world can be related to an infinite, timeless creator. Astronomy serves theology, and questions about the material nature of celestial bodies are easily answered. The heavens are made of a fifth element, perfect and unchanging by definition. Yet the sky itself refuses to honour these philosophical boundaries, and as Europe moves into the late 15th and early 16th centuries, cracks begin to appear in the crystal spheres. In 1572, observers across the continent behold a dazzling new star in the constellation Cassiopeia, visible even in daylight for weeks, and among them is the meticulous Danish nobleman Tycho Brahe, who measures its position night after night and discovers no parallax. That is, the star shows no detectable shift against the background of fixed stars as Earth moves in its orbit, or in the older view, as the heavens rotate. This absence of parallax means the nova stella is located in the supposedly unchangeable. Into this ferment steps Copernicus, whose De Revolutionibus Orbium Coelestium appears in 1543, the year of his death. In its pages, the sun is placed at the near centre of the cosmos, and Earth is promoted from the unmoving anchor of creation to just another wandering planet, circling once per year while spinning on its axis each day. This rearrangement does not necessarily make predictions more accurate than Ptolemy's. Indeed, Copernicus clings to circular orbits and must use epicycles of his own, but it transforms the conceptual landscape, stripping Earth of cosmological privilege and aligning the ordering of the heavens with deeper mathematical simplicity. The true power of this model, however, will only be revealed when Tycho's precise observations pass into the hands of Johannes Kepler, who spends years wrestling with Mars' stubbornly irregular motion until he abandons the venerated circle and embraces the ellipse. With that audacious step, Kepler derives his 3 laws of planetary motion, revealing that planets sweep out equal areas in equal times, and that the square of a planet's orbital period scales as the cube of its distance from the Sun. These relationships, so elegant and unexpected, whisper of an underlying physical principle still unnamed in Kepler's era, and they also open a new kind of cosmic riddle. Why do the planetary distances follow any pattern at all, and what determines that the solar system contains the bodies it does, in the orbits it has, rather than some other configuration? Kepler himself is haunted by that question, and in his earlier work Mysterium Cosmographicum, he proposes that the spacing of planetary orbits can be explained by nesting the 5 perfect Platonic solids between spherical shells, each corresponding to a planet's path. It is a bold attempt to derive the architecture of the solar system from pure geometry, as if divine design has been encoded in shapes glimpsed by philosophers long before observational astronomy reached its maturity. Though later data will demolish this specific scheme, the impulse behind it, to treat the pattern of planetary orbits as a clue to a deeper cosmic logic, anticipates modern efforts to understand why parameters of physics have the values they do. For now, however, the drama of the 17th century shifts from geometry to direct observation as telescopes turn from experimental curiosities into extensions of human eyes, probing realms no naked observer could ever penetrate. In 1609, an Italian mathematician named Galileo swings the telescope toward Jupiter and finds 4 tiny stars that shift position night after night, revealing themselves as moons orbiting another planet, a miniature system that mocks the belief that everything must circle Earth. Then he watches Venus and discovers its phases, changing from crescent to gibbous in a way that makes sense only if Venus orbits the Sun. Turning to the Milky Way, he finds it dissolves into countless faint stars, hinting that the apparently smooth river of light is actually an immense swarm of suns, too numerous and distant to be resolved by the naked eye. Each of these discoveries chips away at the privileged status of Earth and the uniqueness of the Sun, and each raises new puzzles. If myriad other suns and moons exist, might they host their own inhabitants? And if so, what does that mean for the theological and philosophical centrality of humanity? Galileo's enthusiastic promotion of the Copernican system brings him into direct conflict with church authorities, who fear not merely the astronomical implications but the interpretive upheaval that could follow if scriptural passages about Earth's fixity are reread metaphorically rather than literally. The drama of his trial in 1633 is often told as a simple clash of science and religion, but woven into it are subtler anxieties about the loss of a closed, comforting cosmos in which every object has a defined place. Even as Galileo spends his later years under house arrest, however, the mathematical foundation for a new kind of universe is being laid by Isaac Newton, who in the Principia Mathematica of 1687 knits Kepler's empirical laws together with Galileo's studies of falling bodies on Earth, proposing that a single, universal law of gravitation governs apples as well as planets. According to Newton, every mass attracts every other with a force that decreases with the square of the distance, and with this simple inverse square law he can derive the elliptical orbits of planets, the parabolic paths of comets, and even the tides in Earth's oceans. The heavens are no longer a qualitatively different realm, but an extension of the same physical rules that hold in laboratories and orchards. Newton's cosmos, infinite and filled with stars extending without bound, seems at first almost too rational, a majestic clockwork set in motion by God but thereafter running under perfectly intelligible laws. Yet even in this seemingly closed system, unsettling questions lurk. If there are infinitely many stars distributed throughout infinite space, why is the night sky dark rather than blazing with light from every direction? An enigma that moreover, an infinite static distribution of stars under mutual attraction is, in Newtonian terms, gravitationally unstable. Clumps should form and the entire arrangement should either collapse or explode, yet the heavens appear serenely ordered. To preserve stability, some propose a delicate balance or invoke divine intervention, but the underlying problem, that an eternal unchanging universe may be dynamically impossible, remains largely unspoken. Even as these conceptual knots tighten, observational astronomy surges forward. William Herschel, a German-born musician turned telescope maker working in England, systematically sweeps the sky in the late 18th century and discovers the planet Uranus, doubling the known span of the solar system at a stroke, while also cataloguing thousands of nebulae and star clusters that muddy the distinction between fixed stars and diffuse patches of light. With his sister Caroline as collaborator, Herschel attempts the first rough map of the Milky Way by counting stars in different directions, concluding that we inhabit a flattened disk of stars with the Sun somewhere off-centre. The galaxy becomes a structure of which we are part, not a mere backdrop. Yet when he turns his best instruments on certain fuzzy objects, he resolves some into star clusters, while others remain stubbornly unresolved, feeding speculation that these nebulae might be island universes, vast conglomerations of stars far beyond our own. Thinkers like Immanuel Kant and Johann Heinrich Lambert in the 18th century argue that the Milky Way is itself a rotating disk of stars, and that the faint nebulae we see could be other such systems at prodigious distances, a vision of a universe populated by countless galaxies long before observational proof can be secured. At the same time, new technologies allow astronomers to pry into the very composition of celestial bodies. In the early 19th century, Joseph von Fraunhofer uses a prism to spread sunlight into a spectrum and notices dark lines superimposed on the rainbow, a barcode-like pattern whose significance will only later be decoded. When Gustav Kirchhoff and Robert Bunsen in the 1850s and 60s discover that each chemical element, when heated, produces a unique pattern of bright lines in emission, and that the same elements absorb light at those same wavelengths, they realize that Fraunhofer's dark lines are signatures of elements in the sun's atmosphere blocking specific colors. Suddenly, the sun and stars cease to be unreachable fires of unknown substance and become analyzable laboratories whose compositions can be read from afar. The revelation that the sun is mostly hydrogen and helium, first boldly argued by Cecilia Payne in the 1920s, will eventually demolish the old assumption that stars are made of exotic matter. For now, thermodynamics casts a more somber light on the cosmic stage. As the laws of energy conservation and entropy crystallize in the work of Joule, Clausius, Kelvin, and others, the idea emerges that the universe, if finite in energy and governed by irreversible processes, must be heading toward a heat death, a state of homogeneous temperature where no useful work can be done, all gradients erased. This grim extrapolation raises existential questions for Victorians who had grown comfortable with a more or less eternal universe. If everything is running down, was there a beginning when entropy was low, and what set those initial conditions? Lord Kelvin attempts to calculate the age of the Sun based on gravitational contraction, and concludes it cannot be more than tens of millions of years old, an estimate that clashes violently with the geological evidence of an Earth far older and the slow pace of Darwinian evolution. Here, the mystery is not some remote galaxy, but the source of the very light by which we see. The eventual resolution, nuclear fusion in stellar cores, will come only after radioactivity, and Einstein's mass-energy equivalents shatter old notions of matter and power. Until then, the age and energy of the Sun remain puzzles that hint that cosmic physics hides forces not yet imagined. As the 20th century dawns, the tranquil, clockwork universe of Newton is on the verge of being upended by a quiet patent clerk in Bern. Albert Einstein, in 1905, introduces special relativity, which welds space and time into a single spacetime and asserts that nothing can travel faster than light, already implying trouble for Newton's instantaneous gravitational action. A decade later, in 1915, he unveils general relativity, a theory that recasts gravity not as a force, but as the curvature of space-time caused by mass and energy. Massive bodies tell space-time how to curve, and curved space-time tells bodies how to move, to use the later aphorism of John Wheeler. This geometrization of gravity makes new kinds of cosmic structures possible. Space-time can bend, ripple, and even close in upon itself, suggesting that the universe as a whole might have a global curvature, positive, negative, or flat. When Einstein applies his equations to the universe on the largest scales, he initially assumes, like almost everyone of his time, that the cosmos must be static and eternal, and to make such a static model work mathematically, he introduces the cosmological constant, a term that counteracts gravitational attraction at large distances. The equations, left to themselves, would tend to produce either expansion or contraction, but Einstein, guided by philosophical preference more than data, forces a delicate balance. Into this formalism step other minds less constrained by the expectation of cosmic stasis. Alexander Friedmann, a Russian mathematician, and Georges Lemaitre, a Belgian priest and physicist, independently find solutions to Einstein's equations in the 1920s that describe a dynamic universe that either expands or contracts, with matter and radiation diluting or concentrating as the cosmic scale factor changes. Lemaitre goes further, suggesting that the observed redshifts of distant nebulae then being measured by Vesto Slipher may be evidence of expansion, and that the universe might have originated in a primeval atom, a dense, hot beginning from which everything has unfolded. At this stage, however, most astronomers do not even agree on the scale of the cosmos. Are the spiral nebulae inside the Milky Way, or are they stellar systems in their own right, vastly more distant than any star we have yet measured? This great debate, famously staged in 1920 between Harlow Shapley and Heber Curtis, reflects the uncertainty of an era poised on the brink of discovering that the universe is far larger and stranger than Newton, or even Einstein initially imagined, and as we pause among the telescopes and chalkboards of the early 20th century, the stage is set for the next revelations, in which expansion, galaxies, and the very origin of time itself will force humanity to reframe what it means to live in a mysterious universe whose depths are only beginning to be plumbed. The answer begins to sharpen in the heart. As Hubble and his colleagues extend their survey, they notice another curious fact. The light from most distant galaxies is shifted toward the red end of the spectrum, an effect first systematically measured by Vesto Slipher, and when Hubble compares these redshifts to his distance estimates, he finds a rough linear relationship. The farther away a galaxy is, the greater its redshift. Lemaitre had already interpreted such a pattern as evidence for a general expansion of space, not just a Doppler motion of galaxies through a static ether, and now observation pushes the idea from mathematics into physical reality. The fabric of the universe itself seems to be stretching, carrying galaxies along like raisins embedded in rising bread dough. In 1929, Hubble publishes his famous graph of velocity versus distance, and the cosmos that for millennia seemed eternal and unchanging suddenly acquires a dynamic history, a past when galaxies were closer together, and perhaps a beginning when all matter and energy were compressed into a much smaller volume. Yet this suggestion that the universe might have had a definite starting point in time disturbs many, not only because it raises metaphysical questions, but because it offends an aesthetic taste for timelessness in scientific laws. Einstein, who had introduced the cosmological constant to enforce a static universe, reportedly calls his earlier move a blunder when confronted with Hubble's data, though the exact phrasing of his regret is contested. He travels to Mount Wilson, looks through the Great Telescope and acknowledges that the evidence for expansion is strong, but the deepest implications of that expansion will take decades to unfold. Georges Lemaitre, drawing on relativistic cosmology and the new nuclear physics, imagines that in the remote past the entire universe was compressed into a super-dense state, a primeval atom that underwent a cosmic explosion, not in space but of space itself, giving birth to matter, radiation, and time. He presents this idea to the scientific community in the 1930s, but it is met with skepticism and, in some quarters, thinly veiled suspicion that a Catholic priest is smuggling creation theology into physics under a mathematical disguise. Other theorists, like Arthur Eddington, feel a visceral dislike for the notion of a beginning, regarding it as repugnant, while others simply doubt that extrapolating current physics back to such extreme densities is justified. The very early universe becomes a battlefield where equations, philosophical preferences, and quietly, personal temperaments collide. Evidence alone, however, is unforgiving of taste, and during the 1940s a trio of physicists in the United States, George Gamow, Ralph Alpher and Robert Herman, consider the thermodynamic consequences of an expanding universe filled with hot plasma. If you reverse the cosmic clock, they reason, there must have been a time when the universe was so hot and dense that atomic nuclei could not exist, and as it expanded and cooled, light elements like hydrogen and helium would be synthesized in specific proportions through nuclear reactions, leaving a relic sea of photons gradually stretched into the microwave region as space dilated. These photons, they predict, should still bathe the universe as a faint microwave background at a few degrees above absolute zero, a ghost of the primordial fireball. Their calculations, published in 1948, are not immediately embraced, and their prediction of a cosmic microwave background is largely ignored or forgotten, in part because radio astronomy is just beginning, and no one yet has the instrumentation or the intuition to go hunting for such a subtle signal. Meanwhile, an alternative to the evolving universe gains prominence in the late 1940s, the steady-state theory, elegantly developed by Herman Bondi, Thomas Gold and Fred Hoyle, which posits that although the universe expands, It maintains a constant large-scale appearance because new matter is continuously created out of the vacuum to fill the gaps between receding galaxies, keeping the average density unchanged. In this picture, there is no initial singularity, no moment of creation, but they check for malfunctioning electronics, calibrate their equipment, even clean out pigeon droppings from the horn, suspecting that the bird's nesting has introduced unwanted radio emission. Yet the background signal remains. At the same time, just across the Hudson River, a group at Princeton University led by Robert Dick is preparing to search for exactly such a cosmic microwave background, unaware that the Bell pair has already stumbled upon it. When the two groups connect, the pieces fall into place. Penzias and Wilson have inadvertently detected the afterglow of the hot early universe, a nearly uniform bath of microwave radiation corresponding to a black body with a temperature of about 3 Kelvin, just as Gamo's school had anticipated. This discovery, quickly confirmed and refined, effectively kills the classical steady-state model and cements the Big Bang, now rebranded from Hoyle's insult into a technical term, as the leading cosmogonic framework. But in doing so, it also deepens the mystery rather than ending it. For now, cosmologists must explain not whether the universe had a hot dense phase, but how such a phase emerged and why its properties are so finely tuned. Measurements of the cosmic microwave background show it to be astonishingly uniform across the entire sky, with temperature variations of only 1 part in 100,000, implying that widely separated regions of the early universe were in almost perfect thermal equilibrium despite being, in standard relativistic expansion models, causally disconnected. Light would not have had time to travel between them to smooth out any initial differences. This horizon problem suggests that something more subtle than simple expansion must have occurred in the first fraction of a second after the Big Bang. Moreover, quantum fluctuations in the inflaton field, magnified by inflation, see tiny variations in density that will later grow under gravity into galaxies, clusters, and the cosmic web of large-scale structure. Thus, inflation not only resolves horizon and flatness problems, but also provides a mechanism for the origin of the very inhomogeneities that give rise to cosmic architecture. The idea, at first tentative and plagued by technical issues in Guth's original old inflation model, is refined by Andre Linde, Paul Steinhardt, and others into various forms: new inflation, chaotic inflation, that avoid earlier pitfalls and predict statistical features in the microwave background that future satellites like COBE, WMAP and Planck will indeed observe. Parallel to these grand theoretical developments, another, more local cosmic puzzle emerges from the rotation of galaxies. In the 1930s, Fritz Zwicky, working at Caltech, studies the Coma cluster of galaxies and notes that the galaxies within it are moving so fast that, given the visible mass, the cluster should fly apart under its own internal motions. To keep it gravitationally bound, there must be far more mass present than what can be accounted for by luminous stars and gas. Zwicky dubs this unseen component dunkle Materie, dark matter, and suggests that most of the cluster's mass is invisible. His claim, eccentric and rudely presented, is largely dismissed. But in the 1970s, Vera Rubin and Kent Ford measure the rotation curves of spiral galaxies and find that the orbital speeds of stars do not drop off with distance from the centre, as Newtonian dynamics predicts for a mass distribution concentrated in the luminous. Throughout most of the 20th century, cosmologists assumed that the expansion of the universe must be decelerating under gravity, with the rate of slowing determined by the total matter density. But in the late 1990s, 2 independent teams, the Supernovae Cosmology project led by Saul Perlmutter and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, used Type Ia supernovae as standard candles to probe the expansion history and find, to their astonishment, that distant supernovae are dimmer than expected, implying they are farther away than a decelerating universe would allow. The simplest interpretation is that the expansion of the universe has begun to accelerate in the last few billion years, as if some repulsive component with negative pressure, akin to Einstein's old cosmological constant, has come to dominate the cosmic energy density and is driving space apart at an increasing rate. This mysterious component, dubbed dark energy, appears to make up about 70% of the universe's total energy budget, with dark matter contributing about 25% and ordinary matter only around 5%. A humbling partition for beings who for centuries assumed that the tangible stuff of atoms was the norm. The physical nature of dark energy remains deeply obscure. if it is truly a cosmological constant, it may be an intrinsic property of space-time, vacuum energy, whose density remains constant even as the universe expands. But attempts to compute such vacuum energy, at first she and her advisor Anthony Hewish suspect terrestrial interference or instrumentation glitches, and in a moment of wry humour they label the source LGM-1 for Little Green Men, but further scrutiny reveals that the signal is astrophysical, and soon more such objects are detected. They are quickly interpreted as rapidly rotating neutron stars, the collapsed cores of massive stars that have exploded as supernovae, whose intense magnetic fields and rotation beams radio waves like a cosmic lighthouse. Neutron stars themselves had been predicted in the 1930s after the discovery of the neutron, but few had expected their signatures to be so striking, and the existence of matter crushed to nuclear densities, where a teaspoonful would weigh as much as a mountain, forces physicists to extend their understanding of how matter behaves under extreme pressure and gravity. Even more extreme are the black holes predicted by general relativity, regions where space-time curves so steeply that not even light can escape. For decades after Carl Schwarzschild first found a solution describing such an object in 1916, many physicists viewed black holes as mathematical curiosities unlikely to exist in nature. But by the 1960s and 70s, mounting evidence from X-ray binaries, galactic centers, and quasars suggests that these gravitational monsters are not only real, but common. Quasars, discovered as extraordinary luminous and distant radio sources with high redshifts, shine with the output of entire galaxies from regions no larger than the solar system, a feat most plausibly explained by matter spiraling into supermassive black holes and converting gravitational potential energy into radiation. X-ray and gamma-ray satellites detect bursts and flares from violent events. Gamma-ray bursts, for example, whose milliseconds to minutes-long flashes represent the most energetic explosions known, after the Big Bang itself, likely associated with collapsing massive stars or neutron star mergers. These brief, unpredictable outbursts become probes of the distant universe and of physics under conditions unreachable on Earth. Infrared missions peer through dust that obscures star-forming regions, while submillimeter observatories map the cold glow of molecular clouds and the first dusty galaxies. Each wavelength band reveals a different layer of reality, and taken together they show a universe restless, dynamic, and deeply interconnected, where the life of a star in a remote spiral galaxy can leave an imprint on the chemical composition of planets that will form eons later. In parallel with this cosmological storytelling, a quieter but no less transformative revolution unfolds closer to home as astronomers begin to realize that the solar system is not unique, that planets swarm around other stars, perhaps in numbers rivaling the stars themselves. For much of the 20th century, such exoplanets remain hypothetical, their existence debated in the absence of hard data. But in 1992, Alexander Volschan and Dale Frail announced planets orbiting a pulsar, and in 1995, Michel Mayor and Didier Queloz discover 51 Pegasi b, the first confirmed exoplanet around a sun-like star, a hot Jupiter whipping around its star in a 4-day orbit. Soon, if life arises readily given the right conditions, and if technological civilizations can emerge and spread, then over billions of years the Milky Way should have been thoroughly colonized, or at least signaled by now. Yet our radio telescopes, listening for decades, have found no unambiguous signs of extraterrestrial intelligence, and our solar system shows no obvious footprints of visiting probes or ancient engineering. Explanations multiply. Maybe intelligent life is rarer than our anthropocentric intuition suggests. Perhaps complex life requires an improbable chain of coincidences, or technological civilizations are short-lived and tend to self-destruct, or they deliberately remain silent, or they communicate in ways we cannot yet detect. Some propose that we live in a cosmic wilderness, others that we are in a kind of zoo, watched but not contacted. Each hypothesis reflects as much about human psychology as about astrophysical constraints, but beneath them lies a sober recognition. The universe is immensely vast and old, and our tiny slice of space and time offers only a narrow vantage point on processes that may unfold on scales we cannot easily imagine. While the silent galaxy provokes existential questioning, another front of physics gnaws at the intellectual foundations of cosmology. Our two master theories, general relativity, which governs the large-scale structure of space-time, and quantum mechanics, which rules the subatomic world, refuse to be joined into a seamless framework without producing infinities and paradoxes. At their intersection lie regions like the singularities at the centres of black holes and the earliest moments of the Big Bang, where densities and curvatures become so extreme that both theories, separately reliable, break down. Various proposals for quantum gravity proliferate in the late 20th century. String theory, which replaces point particles with vibrating one-dimensional strings and requires extra spatial dimensions compactified at tiny scales. Loop quantum gravity, which attempts to discretize space-time itself into a network of quanta, causal dynamical triangulations and other approaches that model space-time as an emergent phenomenon. These frameworks suggest speculative possibilities: a universe born from a quantum fluctuation, baby universes budding off from black holes, a bounce replacing the classical Big Bang singularity with a prior contracting phase. But as yet, they lack direct experimental support, existing more as mathematically consistent stories than as empirically anchored descriptions. From some of these theories, particularly certain versions of inflation and string landscapes, arises another audacious idea: the multiverse, an ensemble of universes with varying physical constants, dimensions, or vacuum energies, within which our observable universe is just one bubble among perhaps infinitely many. In eternal inflation scenarios, once inflation starts, quantum fluctuations ensure that it never ends everywhere at once. Pockets of space stop inflating and form universes like ours, while inflation continues elsewhere, generating a fractal cosmos of ever-sprouting regions. String theory's landscape of possible vacuum states, each corresponding to different low-energy physics, suggests that different pocket universes might realize different laws of nature. In such a context, the puzzling smallness of the cosmological constant and the apparent fine-tuning of parameters that allow chemistry, stars and life can be reframed as selection effects. We find ourselves in a universe where these parameters take life-permitting values because only in such regions can observers arise. This anthropic reasoning, powerfully unsettling to those who seek deeper necessity rather than environmental contingency, blurs the line between fundamental law and cosmic geography, and raises sharp questions about testability. If other universes are by definition causally disconnected from ours, can the multiverse be more than a metaphysical extrapolation? Even within our own universe, observational frontiers continue to advance, probing ever closer to the Big Bang and ever farther out in distance. The Planck satellite, operating in the early 2010s, maps the cosmic microwave background with exquisite precision, revealing a pattern of tiny temperature anisotropies whose statistical properties encode the initial conditions of the universe, the composition of its matter and energy, and the nature of primordial fluctuations. The resulting power spectrum of these anisotropies matches the predictions of a nearly scale-invariant spectrum of Gaussian fluctuations generated by inflationary quantum noise, strengthening the inflationary paradigm while also providing tight constraints on cosmological. Simultaneously, gravitational waves, ripples in spacetime predicted by Einstein a century earlier, are directly detected in 2015 by the LIGO observatories, as the merger of two distant black holes sends a fleeting shudder through Earth, lengthening and shortening the detector arms by less than 1,000th the diameter of a proton. This triumph opens an entirely new astronomical channel, allowing us to listen to the universe in gravitational radiation. Subsequent detections of black hole mergers and, crucially, a binary neutron-star merger, observed both in gravitational waves and across the electromagnetic spectrum, inaugurate an era of multi-messenger astronomy in which the same event can be studied through light particles and space-time vibrations. These observations not only confirm general relativity in the strong field regime, but also provide independent measurements of cosmic expansion, constraints on the equation of state of neutron star matter, and insight into the origin of heavy elements like gold and platinum synthesized in the ejecta of such mergers. In this way, mergers that once were mere endpoints of stellar evolution become crucial nodes in a web connecting nuclear physics, gravitational theory, and cosmic chemical enrichment. Beneath all these achievements lies a more intangible but persistent mystery: why the universe is comprehensible at all, why mathematical structures devised in human minds to solve parochial problems so often find application in describing phenomena billions of light years away or billions of times denser than anything we can touch. Eugene Wigner famously called this the unreasonable effectiveness of mathematics in the natural sciences. As the 21st century advances, new instruments poised atop Chilean mountains and orbiting above our atmosphere extend our reach still further. The James Webb Space Telescope, unfolding its golden segmented mirror in deep space, peers back to the epoch of reionization, when the first galaxies were assembling from dark matter halos and baryonic gas, revealing surprisingly massive and evolved systems earlier than many models had predicted, hinting that star formation and galactic growth may have been more rapid and efficient in the young universe than previously thought. At the same time, surveys like the Dark Energy Survey and the Euclid Mission map the distribution of galaxies, and weak gravitational lensing shears over vast volumes, attempting to track how dark energy has shaped the growth of structure over billions of years. Subtle deviations from the predictions of standard LCDM cosmology could point toward new physics, modified gravity, or time-varying dark energy. On smaller scales, precision timing of millisecond pulses in pulsar timing arrays seeks to detect a background of low-frequency gravitational waves from supermassive black hole binaries, potentially illuminating how galaxies and their central black holes co-evolve. Even the empty-looking intergalactic medium becomes a canvas on which the imprint of reionization, feedback, and cosmic filaments can be traced via absorption lines in quasar spectra. In laboratories and underground caverns, particle physicists hunt for direct signals of dark matter. Yet the absence of easy answers has never stopped human inquiry, and in the interplay between observation and theory, between the brute facts of data and the imaginative constructions of models, the story of our engagement with the universe continues to unfold, each decade adding fresh chapters that loop back to ancient questions posed under very different skies, by ancestors who could not have named hydrogen or space-time curvature, but whose awe before the night's inscrutable depths was already the first gesture toward the vast tapestry of mysteries that now surround us like the stars themselves.